So let's continue with the chapter 8 by solving the problems. We'll start with the first one, problem 5. A bead slides without friction around a loop-the-loop as shown in the figure below. So we have here the figure, and this is the loop-the-loop. The bead is released from a height h equals 3.5 r, where r is the radius of the circle. What is the speed at point A? So the point A is the top point of the circle. And how large is the normal force on it if its mass is 5 grams? So first of all, we need to determine the speed of this bead at point A on the top. And then we will have to determine the normal force acting on the speed at this point A as well. Okay, first of all, we're going to consider the bead and the loop-the-loop and yours to be one system. And inside the system, all the forces that are acting are conservative. There are no conservative forces acting on the system. Non-conservative, يعني ما في ولا واحدة ما ما في عنا friction. So we have conservation of mechanical energy. Now, if you consider the 2 points, the initial state to be at the point initial when the bead was released at a height h, and let's consider the final point to be at the top of the loop, so at point A. The mechanical energy in the initial state is equal to the mechanical energy in the final state. So K initial plus U initial is equal to K final plus U final. Initially, the bead was released, so it has zero kinetic energy, and its potential energy as measured with respect to this reference that we take for the gravitational potential energy would be equal to m times g times h. That is equal to the kinetic energy in the final point in the point A. It's given by half mva squared plus the gravitational energy of the bead at point A. It's given by m times g times 2r. So it's the radius plus the radius. Because the point was here and now it is up there. So if you just get rid of m could be simplified in all the terms. So we end up with gh is equal to half va squared plus 2gr. So half va squared is equal to gh minus 2gr. Given that h is equal to 3.5 r, so we end up with half va squared is equal to 1.5 times g times r, and so va is square root of 3 times g times r. So this is the speed of the bead at point A. That was the first question. Now the second question is, how large is the normal force acting on the speed on this bead if its mass is 5 grams? And of course, we are still talking about the point A. So as you all know now, if you want to get the value of the normal force, we will need to apply Newton's second law on the bead at point A. So let's apply Newton's second law on the bead at point A. Actually, we don't know how the normal force is. يعني احنا مبدئيا احنا بدنا نشوف شو هي النورمال فورس وكيف هي. Let's just draw n as pointing upwards for the moment and mg pointing downward. These are all the forces acting on the bead when it is at point A, given that there is no friction on the loop. So we apply Newton's second law. It tells us that we have summation over F along the centripetal direction is equal to m times a centripetal. So if we take it to be pointing downward, يعني باتجاه center of the circle, so we take this to be our direction. If we take this to be our direction for the axis, so let's say this is x, okay? So we can write down then at this point that summation over fx is equal to max, where ax is nothing else than the centripetal acceleration. So we end up with minus n plus mg is equal to m times va squared divided by r. So AC, as you all know, you still remember, centripetal acceleration is given by v squared divided by r, where r is the radius of the circle along which the particle is moving. So we are at the point A, so this is why the speed is VA, and the radius of the circle is capital R. So we end up with n equals to m times g minus VA squared divided by R. we take m in common factor, we end up with minus 2 times m times g. So first of all, if we made the numerical application, if we apply the numerical application, we end up with n equals minus 0.098 Newton. And the negative sign, it indicates that the normal force points downward. يعني بما انه طلع لنا هون في negative sign بالفاينل value, بالفاينل result, that means that our projection in this equation was not correct. And so that means that n points downward and does not point upward. So this is it for this problem. We have solved the problem by using the conservation of mechanical energy in the first section and using Newton's second law in the second section. Let's move on with problem 24. A particle of mass m equals 5 kilogram is released from point A and slides on the frictionless track shown in the figure below. So this is the track that we are talking about. It's frictionless. So in principle, all the forces acting on this particle when moving on the track are conservative. And so therefore we have conservation of mechanical energy. We have to determine the particle speed at points B and C. So what is the speed at point B, VB? And what is the speed at point C? So what is VC as well? This is number one. Then we have to determine as well the net work done by the gravitational force in moving the particle from A to C. So how much is WG when the particle moves from A to C? Okay, let's start with the first part. So if you want to determine the speed at point B and at point C, it's very easy to do it if we have conservation of mechanical energy, right? Because the particle was released at the point A, so VA is equal to 0. However, from point A to point B, we have a decrease in the height. And that means that we have a change or a variation in the potential energy. So this variation in the potential energy would lead to a variation in the kinetic energy because the system is isolated. There are no non-conservative forces acting. All forces acting on the particle are conservative. And so we can say that the mechanical energy at point A is equal to the mechanical energy at point B. So kinetic A plus potential A is equal to kinetic at point B plus the potential at point B. Now, given that in this case we have no spring, so the potential energy that we are talking about corresponds to the gravitational potential energy. So let's start with the left-hand side. Ka is equal to 0 because the particle was released. Ua, of course, is different than 0. It's equal to m times g times Ya. Kb is equal to half mvb squared, and ub is equal to m times g times yb. And of course, we take this horizontal line to be the reference for the gravitational potential energy. So we can already reduce m. It cancels out everywhere in the equation. And so we end up with VB squared equals to 2 times G times YA minus YB. So it's 2 times 9.8 multiplied by 5 for YA minus 3.2 for YB. We end up with 5.93 meters per second. So this is at the end of the day, I think this is, yeah, okay, I'll check. I think this is the value of VB. So VB is equal to already this value. Now, let's move on with the second part. We were required to determine as well the speed at the point C. So in the same way, we apply the mechanical energy, conservation of the mechanical energy between points A and C. Nothing changes for the point A. And for the point C, we define its kinetic energy as half mvc squared plus mg YC. Both YA and YC, they are measured with respect to this to the horizontal line, which is the reference for our gravitational potential energy. We do the same. We end up with VC equal to square root of 2 times G YA minus YC. And numerical application, we end up with VC equals 7.67. And this is not of a big surprise it's expected that the speed at point C is larger than the speed at point B, because point C is more lower than point B with respect to A. يعني C أوطى بعد من ال B. فحكما هال difference in the potential energy between B and C راح يتحول ل kinetic energy, and so this is why the speed at point C is larger than the speed at point B. So that was the first question. Now the second question was, determine the net work done by the gravitational force in moving the particle from point A to point C. So the best strategy to solve the second part is to use the work kinetic energy theorem, because number one, we know what are the speed of the particle at point A and point C. So we know delta K, which is one member or one element of the equation. And on the other side of the equation, we have W net. And so W net gives access to the work of all the forces acting in the system. So let's apply the work kinetic energy theorem. It states that W equals delta K. And again, I want to remind you that don't forget that this W that appears in the work kinetic energy theorem, it corresponds to W net, or in other words, to the total work done on the system or on the object by all the forces acting on it. In our case here, we have two forces that are acting on the particle, the gravitational force and the normal force. So W net is equal to WG plus WN. But Wn is equal to 0, because actually the normal is at any point along this track, it's perpendicular to the displacement. So for example, if you take at the point B, it's clear that n points upward, and it's clear that n is perpendicular to the displacement at this point. But if you take, for example, this point in here, at this point, n is actually perpendicular, يعني هي طالعة لفوق، مش vertical، وإنما هي perpendicular على الsurface of contact ما بين الطابق وما بين الsurface. So n is at any point perpendicular to the displacement، لأنه بهالحالة for example هون لحتى نكون دقيقين الانفينيتيزيمال displacement هو بهالشكل هيدا. And so n is all the time perpendicular to the displacement. So its work is equal to 0. What about delta K? Delta K is equal to K final minus K initial. We are looking at the track between point A and point C. So it's Kc minus K, it's Kc minus Ka. Since the particle was released, Ka is equal to 0. And so this is nothing else than half times m times Vc squared. So we end up with the work done by the gravitational force, which is the net work done on the particle moving from A to C, is equal to 147 joule. I just wrote here one other method that we can use in order to determine the net work done by the gravitational force in moving the particle from A to C. We can simply say that since the gravitational force is a conservative force, and we know that the work done by conservative forces is equal to minus delta U, where U is the potential energy associated with the force, then we can say that Wg is equal to minus delta Ug. So it's equal to m times G times Y initial, so Ya minus mg times Y C. And if you just make the numerical application as we have done in here, you will see that we obtain exactly the same result. Wg is equal to 147 joule. So this is it for this exercise. We will move on with another exercise.